Hi everybody, this is Mr. Tegmeyer, and we're going to take a look at thermodynamics, which is a pretty interesting topic. We're going to take that big, hairy, nasty presentation and we're going to break it up into three parts. We're going to break it up into the laws of thermodynamics, which is part one, which is what you're looking at here. Then we're going to break it up into conduction and convection, which is the second part, and finally we'll end up with radiation and insulation. So let's get started. Well, what is thermodynamics? Thermo has to do with temperature, as you can imagine, and dynamics means it's changing. So technically we're looking at changing temperatures, which is what thermodynamics means. But in engineering terms, it's actually the study of the effects of heat flow and work and energy, and really more importantly, it's the movement of thermal energy. And if you go to school and you take engineering as a major, I can't really think of any major that will not take at least one class in thermodynamics. I actually took 2 semester classes or a year's worth of thermodynamics for aerospace engineering. I wouldn't be surprised if you would do the same. Hopefully this slide, thermal energy versus temperature, which you're looking at, hopefully this is some review, but it bears worth repeating. So thermal energy and temperature are 2 different things. Thermal energy, which we commonly call heat, is really just kinetic energy. And it's not something that you can look at a glass, for example, and say it has so much heat. It has to be actually moving from one object to another, and that's how we characterize heat as a form of energy. So it is a kinetic energy. Temperature, on the other hand, we can measure. We typically do that with a thermometer. We measure that in degrees, and that is just the average kinetic energy of the particles in that object. The two are obviously related, and it's important to note that thermal energy or heat is measured in joules. You're all familiar, I think, with the different temperature scales from science all the way back to grade school, I hope, but let's just take a real quick look and review at a couple of different things. So let's look at the freezing point of water and the boiling point of water. So on the Celsius scale, you have 0 and 100 degrees Celsius. For Fahrenheit, it's 32 and 212. And then finally, Kelvin, which we actually use for a lot of our calculations, we have 273 and 373. Important thing to remember is that for each degree increment in Celsius is equal to 1 degree increment in Kelvin as well. So, and some things to remember that an increase in temperature actually increases the kinetic energy or increases the motion. The same thing, the opposite is true for a decrease in temperature. Now, the interesting thing about absolute zero, what you see here, is that's when all kinetic energy is removed from an object. Now, theoretically, and it's debatable, we've never really taken anything to absolute zero. We've come very, very close. But that's when a lot of the math and a lot of our equations really kind of blow up. It's called the singularity. We've never really gotten there, but we've gotten close. So let's take a look at thermal equilibrium. This is something that you would think is common sense, but a lot of people don't really think of it this way. So it bears worth repeating, which you probably know and studying a little bit. So thermal equilibrium is reached when you have 2 objects that are touching and they come to the same temperature. That essentially is thermal equilibrium. When that happens, you lose any ability to do work. So in other words, if you have, let's take a step back, if you have 2 objects that are at different temperatures, you can actually use that temperature difference to create work or do work. That's a lot of times what happens in power plants. You use steam which is at a high temperature, and it expands to a low temperature, and you use that expansion to drive a turbine and create electricity. In this, looking at some of our laws, there's actually 3 laws, and we actually start with the Zeroth Law, believe it or not. And that's because we actually came up with the first and second laws before this. And the Zeroth Law actually is a little bit more basic. So scientists decided to say, well, instead of calling it the third law, because it's so basic, and let's call it the Zeroth Law. It is the only Zeroth Law of anything that I know of. And so what it says is that if 2 systems are in equilibrium with a third system, then the first 2 systems are in equilibrium with each other. So if you look at the 2 objects, object 2 and object 3, and then the thermometer, it basically says that if the thermometer and object 2 are in equilibrium, and object 2 and object 3 are in equilibrium, then it must be the thermometer and object 3 are in equilibrium. Kind of common sense, but it's a law of thermodynamics. So now let's get to the first law. First law of thermodynamics is really just a different version of the conservation of energy. And it basically says that thermal energy can't change form or location. You can't create it or destroy it, but it can move from one system to another, and you can use that thermal energy to perform work. So let's look at an example. So if you have a bicycle pump, if you've ever used one, and this looks exactly like the one I have, if you move that piston up and down a lot, you are doing work on it, and that work adds heat. So that mechanical energy increases the internal energy of the air, and you create some heat. Finally, the second law of thermodynamics says that energy flows from hot to cold. Now you might think, well, Mr. Tegmeyer, I don't know if that's true, because when I put when I go to the store and I buy a 2-liter bottle of pop and I put that in the refrigerator, how does it cool down? Well, what happens is your refrigerator actually uses the temperature difference between the air in the refrigerator and the temperature of that pop, and it pulls the energy from the pop, and it does so in the form of heat. And here it uses a similar kind of example with the frozen pizza. So it says here that if you touch a frozen pizza with your hand, what's happening is your hand is actually warming the pizza. Yes, your hand gets cool, but what you're actually feeling is the pizza pulling energy from your body. So as a result, it's cooling your hand. When you pull it out of the oven, it goes the opposite way. You have a hot pizza and a cool hand, and what you're feeling is the pizza putting energy into your hand. So let's take a look at one more thing with regard to the second law, and that is a word called entropy. And entropy is something that's a little bit mysterious to a lot of people, but essentially it is technically it is the measure of how evenly heat is distributed. And we always go from a low order or an order to disorder or disarray. And basically what that means is the effect of entropy in the second law means that you cannot have anything that is 100% efficient. Because when you go from order to disorder, you can't get that energy back and use it to create work. So here they use an example of firewood. So on the left-hand side, you see it's all stacked nice and neat. It has some internal energy stored within the plant, hydrocarbons in terms of the plant cells. Then when you burn it, oxygen combines with those hydrocarbons and it basically turns to ash. You cannot then take that ash turn it back into wood and burn it again. So that is one example of how the second law of thermodynamics, and specifically entropy, is applied. So remember that things always go from order to disorder, and entropy is always increasing in the system.